Thank you. I am happy to be part of this faculty development program on smart distribution systems organized by, I feel am I audible?
Yes, sir, you are clearly audible, sir.
So organized by the Department of Electrical Engineering, NIT Meghalaya. In fact, the invitation came at a very short notice. So today I'm just going to share some of my knowledge in the related topics with all of you. Before starting my PPT, I just wanted to talk something about smart grid and its associated technologies. So presently, there has been a massive investment across the world in the energy sector, particularly in the upgradation of the transmission and distribution infrastructure. Minimal improvement using a smart grid system is expected to generate significant cost savings. Now, smart distribution system or a smart grid integrates many technologies such as grid control technology, information technology, and management techniques, and thereby achieving a high degree of integration of power flow, information flow, and business flow. Today's smart distributed systems contains renewable energy resources along with the traditional grid so that the power industry meets the efficient, flexible, environmentally friendly, and market-oriented requirements. So initially when the smart grid started, so it was all about smart metering, smart metering and AMI. But, and we had this SCADA control. But today we have gone beyond that. IoT is slowly replacing SCADA. And the main features of a distribution system are, for a smart grid, first of all, it has to be self-healing. That means it has to have the capability of continuous online assessment and automatic recovery. Then a smart grid has to be interactive. That means it has to achieve intelligent interactions between the grid, corporation, and customers. So power line communication is a medium used for this bidirectional flow of information. In fact, this PLC or power line carrier communication has been in existence since the power grids were first invented. But now, in these the smart grids of today, with the application of IoT and other technologies, so these PLC is finding much widespread use. And a smart grid also has to be strong. So it has to be responsive to man-made and natural disasters. That means a smart grid is autonomous and it is self-repairing. So it is designed in such a way that in many cases, if there is a failure of equipment, so it is self-repairing. It can take care of itself. And a smart grid needs to be optimized. So it has to be effective asset utilization, reducing operation and maintenance costs. And moreover, today the pricing offered to customers by a smart grid is dynamic. In some cases, there are times in a day when there is peak load, and there are times when the load is minimal. So sometimes schemes are offered to customers to, avail the power at time of minimal load. So these things are also there. Now in India, the National Smart Grid Mission was launched in the year 2015 to make the Indian power infrastructure cost-effective, responsive, and reliable. So in India, a 20-year plan for integrating the regional, interstate, and intrastate grids were formulated. Now I would like to speak about a few technologies being employed in smart grids. So the first is digital signal processing, or DSP. Now in a smart grid, signal monitoring and digital signal processing is necessary to identify, diagnose, and protect the evolving complex power grid. A modern power system consists of different linear and non-linear loads. Now, in a grid, what happens? A device having a non-linear characteristic absorbing power from a smart grid may be responsible for injecting harmonics that can change the voltage waveform Now ideally the voltage waveform that has been transmitted should be sinusoidal. Now, if we have a nonlinear load absorbing power, so these harmonics can be injected, and as a result, we can be having a non-sinusoidal waveform, and power can be degraded, the power quality. So the performance of a smart grid through monitoring, controlling, protecting, and supervision can be enhanced if DSP is incorporated within its operation. Now, power quality is one of the fundamental issues in the management of a smart grid, where voltage, current, and frequency deviations in the power system are among the major concerns. Some of the signal processing techniques used to overwhelm this smart grid challenge are precision power analytics, time frequency analysis, wavelet transforms, filter banks, metrology, etc. And DSP-based integrators provide for low frequency noise rejection, minimum phase error over the frequency band, accurate current detection, and power analytics to determine grid power quality. DSPs are also used to identify harmonics using discrete FFTs. Now, these harmonics, harmonics are, waveforms, which of multiples of a higher frequency, can result in overheated transformers, false relay tripping, light flickering, etc. Now, as far as the implementation of DSP is concerned, we have to choose between a programmable digital signal processor and an FPGA or ASIC. Now, Texas Instruments and Analog Devices are among the major manufacturers of programmable digital processor, or PDSPs as we call it, while Xilinx and Altera are known for the FPGAs. Now, these programmable DSPs are fundamentally RISC processors. RISC stands for Reduced Instruction Set Computer. So RISC, for example, the processors that we find inside a smartphone, the ARM processor, are also RISC processors. ARM stands for Advanced RISC Machine, which is a more sophisticated RISC processor. Now, if we compare the performance, now when do we use PDSP and when do we use an FPGA, for example? So let us compare the performance in terms of speed. So if we compare the performance of a general purpose digital signal processor with an FPGA, we find that the modern CPUs run in the order of gigahertz. Whereas speed-wise, you might find that an FPGA is very slow, running in, say, just around 60 megahertz. Now, it appears that the clock frequency of an FPGA is less. However, the FPGAs can process data in a massively parallel manner, providing a throughput which is much greater than a programmable DSP. That means the advantage of an FPGA is the parallel processing. But then again, there are a few limitations of an FPGA which can be addressed by using a programmable, which can be used as a programmable DSP. So FPGAs implement, now this main difference is when we use an FPGA, we implement the DSP algorithm in hardware. While we use a PDSP, the programmable DSP, the algorithm is implemented in software. Now coming to IoT. Now application of IoT in a smart grid allows measurement of different types of electrical parameters and to control and monitor the equipment in the grid from a remote location. In IoT, physical devices, sensor appliances, and other objects communicate with each other without the need for human intervention. Now, within an IoT, wireless sensor networks throw fresh challenges so far as software.
Sorry for the interruption. Can you share the PPT, sir?
Oh, yes. Let us start the. Oh, it's getting late. Okay, sure. Okay. Let me start the PPT. Share the PPT.
Yes, sir. Thank you, sir.
Okay. Let me see how to. Where is it? Okay, just a moment. Okay, let me start. Okay, my presentation. Okay, so my topic for today is smart grid IoT and big data analytics. Is the PPT visible?
Yes, sir. Can you make it full screen, sir?
Oh, yes. Okay.
Yes, sir. Thank you, sir.
Okay. So the topic for today is smart grid IoT and big data analytics. So just a minute. So now the coming to IoT. The IoT, the Internet of Things has arrived and it is prevalent everywhere. Now, we heard things about such as smartwatch, smartphones, in IoT devices. So, the IoT industry has a long way to go in terms of overall security. So, many of today's IoT devices are rushed to the market with basic security and privacy protections. However, it has future scope. Okay. Now, the Internet of Things refers to a system of interrelated, interconnected objects that are able to collect and transfer data over a network without human intervention. So, just a moment. So, as I was saying, just a moment. So now I won't dwell much on IoT since I think so now actually IoT is nothing but where things are, it's communication between inanimate things, between machines. So this thing can be a solar panel, it can be a connected automobile. So normally IoT is connected with sensors. So these things sense the information in the environment, say temperature, pressure, humidity, and all this. Okay, and these are an IoT by itself generate a huge amount of data. Okay, so normally the data that is generated, it depends. For example, we might have an IoT system where we are just monitoring say a few solar panels, 10, 15 solar panels. Now, in this case, we can simply connect some sensors to those solar panels, okay, and maybe we can connect some, say, Arduino boards, and it can send the information locally. It need not be connected to the internet as such. No, it can be connected to a machine which is monitoring all these devices through a wireless network or through any private network, and the data can be processed. Now, in many things, especially in a grid, for example, the amount of devices, the amount of sensors being employed is massive, and the data generated is also massive. So what happens is, to process the data, we need, first of all, the data goes to the cloud, to the internet. And secondly, we need to some specialized analytical tools. For example, if the data is very huge, we need to make use of big data technology in IoT. So we can say that cloud computing and say big data analytics are also closely associated with IoT. Now, in an IoT ecosystem, it's a connection of various kinds of devices that sense and analyze the data and communicate with each other over the networks. So in an IoT ecosystem, the user uses smart devices such as smartphones, tablets, sensors, etc. to send the command or request to devices for information over the networks. The device responds and performs the command to send information back to the user through networks. So this is an example of an IoT ecosystem. We have a smart grid, smart lighting, smartphone, smart energy. We have users getting the information from the IoT system. There is this sensing, there is embedded processing, connectivity. Let me go to the next slide. Now, coming to the IoT for smart grids, So these smart grids, IoT plays a major role in smart grids, and IoT can be found in, say, in the power generation level, in the power distribution level, and in the power transmission level. So now, coming to a smart grid, uh, smart grid, it has got different power sources are integrated in a smart grid. For example, you have this conventional power, you have solar power, you have wind energy, and other sources of power. So now let us see how IoT can be implemented in wind energy. Now, wind technologies are evolving rapidly in terms of efficiency and scale. So now, wind energy is a major source of power, along with the normal the energy sources we have, along with solar energy. Now, by using IoT, we have the owners of the say, which can be farm owners. They are able to conduct accurate and preventive maintenance. And in an IoT system, we apply machine learning, data mining techniques. Now, data corresponding to wind turbines are collected in real time. Now, here, as I said, as I have repeated before, IoT systems are cost effective in terms of the SCADA systems which were implemented earlier. So now, using IoT systems, we can, perform a real-time monitoring of the infrastructure of the wind energy. So now, as I said, in a, say, wind energy generation plant, the generation can be monitored in real time, and the decisions such as shutting down the turbine, if required, can also be taken. So normally, when we come to IoT, it consists of an embedded system containing a microcontroller, along with sensors, along with the transceivers, receivers and transceivers. So here in this case, normally, as I said, when we monitor things on a real time, we may sometimes make use of an RTOS. So RTOS stands for a real-time operating system. So in a real-time operating system, what happens? Things can be processed parallel in a microcontroller. Now, the wind turbine contains components such as blades, rotor hubs, pitch systems. And the IoT controller contains sensors and actuators. So these sensors report the health and performance of each of the intrinsic components. So the sensors in an IoT system for a wind turbine can be environmental sensors, mechanical sensors, electrical sensors, temperature sensors, and fluid sensors. So cyber physical devices are integrated to connect the physical layer of the wind turbines to the cyber layer using a network infrastructure. Now, the turbines of a farm are equipped with IoT-based embedded systems. Distributed intelligence services employing wireless sensor networks will come to wireless sensor networks shortly. And machine-to-machine communications is carried out with a cloud-based network. And the data transfers are internet-enabled, and it communicates to servers using open communication standards. So this is one area where IoT is employed. Next, we come to solar energy. Now, solar energy has the largest potential for power generation from renewable energy. In fact, India is laying a great emphasis to solar energy. So solar energy refers to radiant heat and light of sun, and solar energy can be harnessed through the incorporation of photovoltaic technologies. Now, these solar energy can be installed as a distributed generation. It can be obtained from solar parks or concentrated solar power systems. So, Now, coming to these photovoltaic cells, okay, in a solar plant. Now, the solar power plant consists of solar panels, which are photovoltaic arrays, wiring, switches, mounting system, and inverters. Now, a solar plant, apart from, it also contains a storage unit. So, in fact, it contains a battery bank. So, it contains a maximum power point tracker. It has got a GPS solar tracker, solar irradiance sensors, anemometer, roof. These solar panels can be roof mounted, or it can be integrated in a building. So these photovoltaic system grids are either connected online, or they can be also standalone. Now, output of a solar photovoltaic plant relies on the ambient temperature and sunlight radiation intensity. So the no, I'm not sure. How do you display it? Okay. Just okay, let me give you the next slide. Okay. Now, in the case of solar plant, IoT helps in sharing data gathered from the PV sensors in real time. So it can predict, this grid scale coordination of uncertain solar production and energy storage. It can monitor the performance of the arrays, and it can also carry out troubleshooting and conducting on-time maintenance. So next we come to IoT in transmission level. So the transmission level is a critical part of power systems which ensure a reliable supply of demand. The integration of IoT in transmission level is very important in two aspects. First is that the implication of IoT in the improvement of congestion management, and the second is the impact of IoT in maintaining system security. So now the this IoT infrastructure contains IoT-equipped intelligent electronic devices, or IEDs. So they can be installed in the transmission sector to inform the operator of the electrical state of the lines, such as loss disturbances. And then we have these phasor measurement units, which can determine the magnitude and angle of voltage and current at a specified point of the line, taking advantage of the GPS system for time synchronization. Now, apart from that, we have got, if you look at the difference between IoT and using IoT and SCADA. So this phasor measurement unit is able to report measurements with a resolution of about 30 to 60 measurements per second. So if you compare it to an older SCADA system, so it is found that SCADA reports one measurement every 2 to 4 seconds. So it can be seen that there's a massive improvement in the scale of monitoring. Now, these overhead lines are vulnerable to many natural disasters. Harsh wind and storms, these conditions may lead to, these transmission lines getting damaged. And this can cause exertion of asymmetric pulling force to lights, which may lead to leaning of towers. Towers may also be damaged. So these factors cause damage to overhead lines, which has the risk of shutting down the operation. Now, in addition, the transmission system is scattered in a vast area of land, which can be remote and difficult to maintain and monitor. So the incorporation of IoT can help in removing these damages, in fact, in monitoring these damages and removing these damages caused by such, natural phenomena. So the data in order to do that, the appropriate data must be acquired in real time from the sensors which are placed in those conductors or towers, etc. So, some of the sensors which are placed in the transmission level are tower deviation sensor, which can sense the deviation of towers. Meteorological sensors, which are in fact temperature and humidity sensors. Then we have the wind speed sensor. We can monitor the speed of wind, which can alert us to the possible damage that can be caused to the transmission lines. Then conductor acceleration sensor, sag sensor, which is an important sensor for transmission lines. And then we have these current leakage sensors. Now, next we come to IoT at distribution level in a smart grid. So similarly, that all critical points of the distribution network must be equipped with IoT infrastructure. So first is the installation of AMIs. So AMIs, as we know, stand for advanced metering infrastructure. So this is the first step towards the implementation of a smart distributed grid, from the consumer's point of view. So now here the communications network is counted as one of the most crucial parts in AMI systems. So this communication infrastructure, which I had mentioned earlier, for example, it is this power line carrier, PLC, it provides a bidirectional, consistent and secure connection between servers and data collectors, customers and other beneficiaries. So, this communication infrastructure can be implemented differently with respect to local condition and as per the budget. Now, so the benefits that we get from by employing IoT at the distribution level is, so we can perform online supervision on consumer patterns of consumers, consumption patterns of consumers. So, this smart grid that we have, as I said, it offers dynamic pricing to consumers. So consumers are a very important part of the smart grid. Then from this IoT infrastructure, we can have intelligent control of generation and consumption of energy. It can detect problems in low voltage transmission lines. It has the capability to implement emergency demand response programs. And as I mentioned before, smart grid, a smart distribution system is supposed to be self-healing. So with the help of IoT, we can implement these self-healing schemes. Then we can do power loss management and remote monitoring and controlling. Okay, so this was about the grid. Now I would like to speak about the wireless sensor network. So these wireless sensor networks, essentially, every IoT system may not have a wireless, sensor network. For example, if we just, say, as I said in my previous example, if we are, monitoring just, solar plants, a few solar panels, which are, distributed a few meters apart, we can install some what we call microcontrollers, some Arduino boards, for example. Yeah, we can transmit directly to a controlling center. So in such cases, wireless sensor nodes are not that important. But in a smart grid, for example, wireless sensors are invariably deployed. So these sensors are, they are transceivers. They have got a microcontroller. They've got a processor along with receiving and transmitting equipment, along with, of course, sensors. They are usually scattered in a sensor field where each sensor has the capability to collect data and route back to the sync gateway. So it also contains a sync and gateway. So this wireless sensor network, they are composed of a number of sensor nodes which are densely deployed. Okay. And these sensor nodes are self-configured, and these are infrastructureless wireless networks. And these nodes, wireless sensor nodes, and sometimes they are also called modes, MOTES. So these monitor physical or environmental conditions such as temperature, sound, vibration, pressure, motion, or pollutants. And they cooperatively pass data through the network to a main location or sink where the data can be observed and analyzed. So in a wireless sensor network, apart from the nodes, there is a central controlling structure which we call the sink. So the data collected from the sensors are eventually passed to a sink, which will then pass it to, say, we can be pass it through the internet to the control center. Now, this cooperatively passes data means we'll come to the topology in the coming slides. So, in many cases, every sensor node has to play a role in passing the data transmitted by its neighboring nodes. I mean, it's a question of, star topology or mesh topology, like we have in the network. So these sensor nodes are usually transceivers scattered in the sensor field. So they use their processing capabilities to locally carry out simple computations and transmit only the required and partially processed data. That means the data that they gather through the sensor is also partially processed. Okay. Now, the processor in the wireless sensor node is comparatively a very less powerful processor. And one of the main issues in a wireless sensor network is the conservation of power. So one thing is the receiving and transmitting consumes power, along with the processor. Processing also consumes power. So usually we find that the processor present in a wireless sensor node, it works at low frequency, comparatively lower frequency, so that less power is consumed. Now, the sink may communicate with the task manager or the end user via the internet or satellite or any type of wireless network. So as I said, these wireless sensor nodes pass the information to the sink. So it is the responsibility of the sink to communicate to the end users to the control center, which is utilizing this wireless sensor nodes. Now, in many cases, the sink can be directly connected to the end users. So it is not necessary that the sink is connected to the internet. Wireless sensor network can also be localized, where a person is directly processing data from the sink. Okay, coming to the next slide. So the wireless sensor nodes consists of 5 main components. So the components of a wireless sensor nodes are, they contain a microcontroller unit. So normally it is the microcontrollers which are mostly used in the wireless sensor nodes. ASICs and FPGAs have also been tried out, but mostly it is the microcontroller. Then we have got the transceiver unit. Transceiver unit is the transmitter receiver unit. So this transceiver unit, design of the transceiver unit is most important because this is the component of the wireless sensor network which consumes the most power. Then we have the memory unit. Okay, the memory can be an on-chip memory as part of the microcontroller, or it can be an onboard memory, external memory, which is present on the microcontroller board. And then we have the power unit. Okay, the power unit is usually a small battery and of less capacity, and we also have renewable power units like solar energy, and these things are also utilized in the wireless sensor nodes. And above all, we have the sensor unit. So it is responsible the sensor unit to detect the information, pass it to the microcontroller unit, which is again processed at the microcontroller unit, and it is passed to the sink to the nearby nodes. Now, coming to the microcontroller unit, the activities of the microcontroller unit are data processing, controlling of other components in the node. So it may consist of, as I said, on-chip memory, or it can be associated with memory, integrated onboard memory. Okay, so the microcontroller unit manages the procedures that enable the sensor node to perform sensing operations, run associated algorithms, and collaborate with other nodes through wireless communication. Now, as I have mentioned before, in a wireless sensor network, this collaboration with other nodes is very important. It's a very important feature in a wireless sensor network. Now we come to the power unit. So the power unit is the most critical component of the wireless sensor network. So power can be stored in batteries, which is the most common. So it can be rechargeable, or it can be stored in capacitors. So natural sources such as solar power, wind power can also be utilized to power the wireless sensor network. And as I have said before, the most power is consumed by the transceiver unit. Okay, so this, as I said, this most power being consumed by the transceiver unit has some implications, has some serious implications in a wireless sensor network. Okay. Now, coming to the sensor node, the sensor node is responsible for, as I said, relaying information received from neighbors. So now, as I said, the low power communication limits the range of the a particular wireless node. So it is not that one wireless node, if it is located at say far away from the sink, so it is not possible for that particular node to communicate with the sink directly. So we require a multi-hop communication strategy where one node passes on the information to the next node, which passes out to the next node, and so on until it reaches the sink. So normally we do have, suppose in say we have a wireless sensor network, which is where the nodes are scattered nearby. So in those cases we can implement this star topology where the node communicates with the sink directly. But usually in most WSN installations where they are spread over a wide geographical area, the multi-hop communication scheme is utilized. Now this routing protocol determines the way the information is forwarded to the neighbors. Now this routing, again coming to routing. So as I said, this wireless sensor network has to perform within certain constraints. There is a constraint of power, there is a constraint of processing power, and there is also a constraint of memory. So memory is also a constraint. So as we'll see later, we use operating systems and softwares with a very small footprint. So normally the routing protocol is not like the normal routing protocol that we implement in a normal computer. Okay, so it is a miniaturized routing protocol. So the and as I said, wireless sensor network can also implement an star topology if they are nearby. If there is enough power so that node can transmit directly to the sink. So star topology can also be implemented if the transmission ranges of all sensor nodes are large enough. Then sensors can transmit data directly to the centralized base station. So usually, when we implement star topology in a wireless sensor network, so it is usually confined to a smaller geographical area. Now we come to the protocol stack. So it implements a reduced protocol stack. Normally we have this 7-layer protocol, this ISO OSI level protocol. So here only 4 layers are utilized. So first we have the physical layer, which addresses the needs of simple but robust modulation, transmission and receiving techniques. Then we have the MAC layer, the medium access control layer. Then we have the routing layer, which takes care of routing the data. And then we have the application layer, which hosts the application software. So here, we don't make use of the, there is no presentation layer, there is no session layer, there is no transport layer. So now we come to the constraints of the wireless sensor networks. So the properties of individual sensor nodes may pose additional challenges to the communication protocols. So particularly in terms of energy consumption. Okay. So normally the sensor nodes, they carry limited power sources. So we have these batteries, which can be replaced, which need to be replaced or recharged. And in many situations, we have these wireless nodes where when they stop working, they are simply discarded. So some nodes are simply discarded once energy is depleted. So a focus of power consumption and throughput is one of the major research areas in wireless sensor networks. Then we come to node deployment. So node deployment is another factor which needs to be considered in developing these wireless sensor network protocols. So, the position of the sensor nodes, they are not predetermined. The situation can be such that you don't have a choice of, placing the nodes at a predetermined location. You cannot engineer it. So this leads to, random deployment of the sensor nodes, and sometimes these are deployed in inaccessible terrains. So these random deployment requires self-organizing protocols. That they must self-organizing means they must configure themselves, operate and collaborate with other nodes. And as I said, they should also adapt to failures, changes in environment without human intervention, actually. So the many sensor networks, once, as I said, once they're deployed, they remain unattended. Okay, and they have to perform in an autonomous fashion. Now let's have a look at an operating system which is widely used in wireless sensor networks. So there is an OS called Tiny OS, which is mostly used in the wireless sensor networks. Okay. Now, as I said before, I mean, wireless sensor networks means the nodes that we have. You know, this, for example, to give an example, in the common Arduino boards that we use. Okay. So there is something called Arduino BT. BT, I think, stands for Bluetooth. So this is so the memory size is less, resources are less in these. Processing power is less in the wireless sensor networks that are deployed. So the tiny operating system, the size of the operating system is fewer than 400 bytes. Okay, so it's a flexible operating system, and it supports event-driven concurrency model. So in fact, in most wireless sensor network applications are event-driven. So now this tiny OS is implemented in a language called NESC. NESC is a subset of the C language. So, this tiny OS has enabled innovation in sensor networks in a wide variety of applications. Now, this version of Tiny OS, this is currently the third generation of this Tiny OS employs a component-based programming model. Okay. Now, component-based programming model means, to make this clear, so it consists of software components. Component means actually going back to that, in computers, first we had these, assembly language programming. Okay. Then Unix was, then the C language developed, higher level languages developed. Okay. Unix was written the C programming language. Then we had object-oriented programming. So, as I remember, this component-based programming was a big hit in the 1990s. So, it came in the 1990s. So, Microsoft had introduced the COM, COM. COM stood for Component Object Model. Okay. In Java, you have these Java beans, which are components. Now, a component is, it is a kind of a software which is, in compiled form. Okay. So it can be part of a process in a computer program. It can be in a different process, or it can be distributed. Okay, like we had this distributed component object model like COM. Okay, there are some architectures like Corba. So basically, component means it's a, there is a certain way of communicating with a component. Okay, it has got a certain protocol. So normally components, you have something called interfaces. They expose certain interfaces through which we can interact with the functionality of the component. So it has got a programming framework for embedded operating systems. And just to get an idea, the typical application size, if we develop an application in Tiny OS for a wireless sensor network, the overall application size is around 15 kilobytes. And of that 15 kilobytes, the OS occupies 400 bytes. So in Tiny OS, the largest application, which can be a database like query system, it's about 64 kilobytes. Okay, so we have covered, IoT in general, IoT, then IoT, application of IoT in smart grids, okay, then wireless sensor networks, which are an important component of IoT. And then we had to look at Tiny OS, which is an operating system, widely used in IoT. So now the Internet of Things generate a huge. This Internet of Things, if we have in the smart grid, so it generates a huge amount of data per second. Okay. So managing the flow and storage of this data, it is a tedious task for enterprises. Okay. So, so normally this data that is generated, okay, is sent to the cloud. Okay. And normally we used to have, we have to utilize technologies like, say, big data. To process this huge amount of data which is generated. Okay. So, next topic, let us come to Hadoop. Okay. So, just a moment. Okay. So, just a moment. Okay. Okay. So, as I said, the machines in an IoT setup generate a huge amount of data. So the amount of data generated is massive and is comparable to data generated from social media sites. For processing this massive data, we usually turn to the field of big data. So big data involves large scale, big data is nothing but large scale parallel processing of data using commodity machines. So, as opposed to using very powerful servers, here we use a large number of commodity machines performing computations in parallel. Okay. So it has been seen that a cluster of commodity machines can process this data with less cost and higher throughput than a monolithic high-end server. So while using a high-end server, for example, when the processing power of the machine becomes inadequate, we either replace the server or we scale up the server by replacing it with another server of very higher capacity. Now, in the distributed processing, what we need to do is we simply need to add more commodity machines to the cluster. So this Google, previously for processing large amounts of data, they were using a technology called MapReduce. So MapReduce was a programming model being used by Google for processing the huge amount of data, which was, in terms of terabytes and petabytes. Now, Hadoop is an open source version of MapReduce, which was created around 2006. So, as in, the big data, Hadoop data is stored across a cluster of machines, using the Hadoop distributed file systems, which will come to soon. So, the key distinctions of Hadoop are, it is accessible. Hadoop runs on a large clusters of commodity machines or on cloud computing services such as Amazon's Elastic Cloud Computing. So, one can, if you have your own infrastructure, you can install the Hadoop, platform in your own office or environment, in your own organization. But Hadoop can also be accessed through the cloud. Okay, so there are many cloud service providers which are, provide Hadoop services. Amazon Elastic Cloud is one of them. And actually, the more popular implementations of Hadoop are implemented on by two cloud service providers called there's Cloudera and Hortonworks. Okay. There is this Cloudera through which which provides you these Hadoop services. And apart from Cloudera, Hortonworks is a very popular cloud service for Hadoop processing. So it is robust because it is intended to run on commodity hardware. Hadoop is architected with the assumption of frequent hardware malfunctions. So it can gracefully handle many such failures. That means Hadoop contains a large number of machines. So if one machine goes down in the cluster, another machine takes up the responsibility. It is scalable. Hadoop scales linearly to handle larger data by adding more nodes to the cluster. And Hadoop is simple. It allows users to write efficient parallel code. If you don't mind, I'll just like to take a just 2 minutes break.
Yes, sir, sure, sir.
Yes, sir. Are you going for any demo? Yes, Santanu sir, can you hear me? There is a network problem or Kavalya?
No, sir, I think he's not. Yeah, now he can hear you. Now he can hear you.
Yeah, Santanu sir.
Yes, yes.
Are you going for any kind of demo?
Actually, this demo couldn't materialize because of this in a hurry. Mostly it is in slides.
Okay, fine.
It is,
Fine, please go ahead. Okay. That you told that day that you will
yeah, no. Actually, this because of the hurry, some configuration problems, but I would like to do it in future.
Okay, sure.
Because I have to connect to a remote machine from this Linux and Windows.
Okay, fine. No problem. Thank you.
So, speaking about Hadoop, so in distributed systems versus monolithic servers, as I said, mentioned just now, in a monolithic server, to increase the capacity, we have to scale up. Whereas in a distributed systems, we have to scale out. So just to give an example, a high-end machine with 4 I/O channels, having a throughput 100 megabyte per second will require 3 hours, to read a 4 TB data set. With Hadoop, this same data will be divided into smaller blocks that are spread among many machines in the cluster via the Hadoop distributed file system, HDFS. So with a modest degree of replication, so actually, you find out that using a cluster of commodity machines, instead of using a high-end server, first of all, these cluster of machines are more powerful and they are more cost-effective. Okay, they turn out to be cheaper. A cluster of commodity machines turn out to be cheaper than a single high-end server. Now, let us just briefly describe how data is processed. Used. This Hadoop, unlike SQL, SQL, deals with structured data. So SQL deals with the database where data is structured, where data is organized into relations, schema, and tables. Hadoop can deal with structured data, but usually Hadoop deals with unstructured data. It can be data which is a huge amount of data which is generated by an IoT system in a smart grid. It can be data generated from the social media sites. So these are not in any structured format. They are just in text format. They can be comma separated. They can be tab separated, space separated. Now, what Hadoop does is it organizes this entire data into a key value pairs. Okay. So a fundamental tenet of relational databases is that data resides in tables having relational structure, defined by a schema. So large data sets are often unstructured or semi-structured. Okay. So Hadoop uses key value pairs as its basic unit, which is flexible enough to work with less structured data types. So, data can be in any form, but ultimately it is transformed into a key value pair for to be processed. So this MapReduce paradigm, MapReduce programs are executed in two phases called mapping and reducing. So the mapper is meant to filter and transform the input into something that the reducer can aggregate. So once we get a data, we pass it to a map function, which organizes into key value pairs, which is sent to the reducer, which can aggregate over. So the MapReduce framework was designed, after a lot of experience in writing scalable distributed programs. In scaling distributed work, okay. Now, normally the input to the application must be in key value pairs. Just a moment. Okay, let us, since we are not performing an example, this might be confusing. Let us see how this Hadoop is organized. Okay, since we are not doing any program. Okay. So, coming to the building blocks of Hadoop, on a Hadoop cluster, we have these set of daemons: name node, data node, secondary name node, job tracker, task tracker. So if any of you is not aware what a daemon is, so daemon in Unix terminology is an invisible process. There is no name of the process. It is an invisible process running in the background. So Hadoop consists of a name node, data node, secondary name node, job tracker, task tracker. Okay, let us see their functions. Okay. So the name node employs a master-slave architecture for both distributed storage and computation. So basically, name node deals with the storage of information. Now, actually, as I said, the Hadoop system can process huge amounts of data, okay, terabytes and petabytes. Now, what happens is, suppose we have a data running in 2 terabytes or petabytes. Now, for the user who is using the Hadoop system, to that user, it appears as if it is a single file. 1 petabyte of data is a single file. So it interacts with it like this, like it interacts with a single file. It is the responsibility of the Hadoop system to split that file and store it in the various machines on the cluster. So this name node is the master of HDFS that directs the slave data node daemons to perform the low-level IO tasks. So the file system that is used in Hadoop is called Hadoop distributed file system. Okay, I've mentioned. I failed to insert the distributed here. So as I said, a distributed file system stores data across machines distributed on a network. Now the function of the name node is memory and IO intensive, so it typically doesn't store any user data or perform any computation. So what it means is that we need a dedicated machine for a name node. Now data node is the slave machine where the blocks of the actual files will be stored. Okay. So when we want to read or write a file to an HDFS file, the file is broken into blocks, and the name node tells the client in which data node each block resides in. And the client then communicates directly with the data node daemons to process the local files according to the blocks. Data node may communicate with other data nodes to replicate its data blocks or redundancy. That means the data. I mean, information that is stored in the machines in a cluster. Duplicate copies are stored in other machines, so that the failure of one machine will not will not prevent the customer from accessing the data. And data nodes are controlled by the master. They are constantly reporting to the name node. And the secondary name node is a backup to the name node. That means if the name node goes down, it is the responsibility of the secondary name node to take over the functionality of the name node. Then we come to the job tracker. Now, name node and data node is for storing information. Job tracker and task tracker is for storing the applications which process that information. So it is the daemon which acts as a liaison between the application and Hadoop. So job tracker determines the execution plan by determining which files to process, assigns nodes to different tasks, and monitor all tasks that we are running. I mean, should a task fail, the job tracker will automatically relaunch the task, possibly on different machines. So as I said, if one machine fails, it is the responsibility of the job tracker along with the name node to assign the same responsibility to another machine in a cluster. And similarly to the name node, where we assign a dedicated machine to a job tracker. Now, the tasks, the actual execution are carried out in the task tracker. So the task tracker is responsible for executing the individual tasks. It communicates from the job tracker, and it regularly sends signals to the job tracker. So if a job tracker fails to receive a signal from a task tracker within a specified amount of time, it assumes that task tracker is down. So it assigns the responsibility to a different. Okay, so next we just talk about HDFS, the file system being used in Hadoop. So as I mentioned before, HDFS is a file system designed for large-scale distributed data processing under frameworks such as MapReduce. And in HDFS, as I mentioned earlier, we can store a big data set, say 100 TB as a single file. I mean, for the user, he'll interact with that data as if he's interacting with a single file. Okay. So that data is distributed over multiple machines to enable parallel processing. And this, it provides what you call location transparency. The user is unaware that it is where it is the information will be stored. To him, it appears as if it is interacting with a single file. And the commands, HDFS commands, are very similar to Linux commands. So they are preceded by the command HDFS DFS. In fact, today I was planning to give a live demo. Somehow it didn't materialize. So today I have come to the end of my presentation. So we have covered IoT, smart grid, and this wireless sensor networks, and there's Hadoop. So thank you. I have come to the end of my presentation. Any questions?
Participants, if you have any questions, you can unmute and ask. So, sir, it seems there are no questions from the participants.
Hello.
Yes.
We'll just wait for just 1 minute, sir. Sir is correcting.
Hello, sir. Sir, am I audible, sir?
Yes, yes, yes.
I am Krishna Kumar calling from Jackson's Institute of Technology. It was in Coimbatore State, sir, Tamil Nadu State.
Right.
Sir, instead of Hadoop, can we use the blockchain technology? Because in Hadoop, it retains the originality in case of server fails, and it actually transfers the data to other machine. So it was like that only. So blockchain also retains the originality. In case of any failure comes from, it will retain the original data to the other one.
Yes,
So
yes, yes, yes. Actually, I was simply talking about the earlier form of Hadoop. Now, many new technologies have been integrated to Hadoop, and I couldn't time to talk about artificial intelligence, machine learning, all these things. Maybe I should have stuck to a single topic. So, okay.
yeah,
Yes,
sir.
yes, sir. Thank you. Thank you. Any queries, any questions you want to have? He has given particularly on the wireless sensor network, all those things. And with a time limit, maybe he could not show the demonstration. Otherwise, it will have a more experience kind of thing. Anyhow, but in future, we'll be again taking your support in this regard. As the NIELIT Shillong is very nearer to us, and definitely we'll go with some research collaboration. Thank you all.